this section, I want to talk about the optical properties. It's the last piece of the physics that we're going to be doing. Essentially, it's a very simple section of work, and it's an introduction to stuff that those of you going on with are going to be doing in the years ahead. Now, you may or may not have heard, I'm sure you have heard of the concept of photoelectric effect. You've heard of waves, light coming in waves, but now we're going to look at the duality of light. It's got a wave and a particle element to it. Now, the easiest way to think about this is if you are in the sea and the waves come at you, you feel the energy of the wave as it passes by you, don't you? Well, in essence, we say light has got the same kind of properties, because just like a wave coming at you in the sea is going to hit you and knock you over, I'm not talking about a breaker, just a normal wave. It's going to hit you and you're going to feel that motion of the water. Now, similarly, we have got this duality. We've got light. I call it basically, it's schizophrenic. We've got light and we've got the wave side of light. Let me make that a little bit neater. The wave side of light, right? Now, wave, remember, we can reflect waves. That's a mirror. Angle of incidence equals angle of reflection. We can also, I've got here, refract. Remember Snell's law? Light bends its thingy like that. The angle of refraction, okay, and refractive index of different materials. So as the light comes into a thicker, optically dense material, it slows down and then it speeds up again when it goes out. That's the refraction side of light. Then we have the diffraction side. These are all things we can do with waves, correct? Then we have diffraction. Diffraction is when it passes through an opening and you get your wave front doing that as it goes through around an object, impeding its progress. Then you also, last of all, you got interference. Interference, and remember, what did we get? We got destructive and constructive. I know this is the whole teaching grandmother to suck eggs, but those are things that we see with light waves, okay? We see the same thing with waves in other medium, okay? You do physics, you're going to do waves going up solid bars of metal and things like that, propagation of waves and things like that. Now, when we look at this, we say, but hold on, these waves have also got an energy associated with them, right? So they will knock me over. Now, light exhibits the characteristics of the wave very strongly so, but, and here's the rub, the photoelectric effect illustrates the duality of the light, because it is also a particle. It is also a particle. It's got a particle nature to it. How do we know this? Well, basically, this comes down to what we call the photoelectric effect. Right? And what is the photoelectric effect? Well, if you remember, or if you've seen, you'll see on those model cars often, you see like a little black panel sitting on it, and you see it in the top of calculators as well sometimes, where they charge the battery using light waves. And they're called photovoltaic cells you get as well. Now, what happens here is that when we have a specific kind of material, okay, we have this kind of material, let me just get back. Okay. And we have what is called here incident. Okay. It's not spelling. Incident light waves coming in. What happens? This hits this material. Part of it gets reflected back, but let us say the material is black, which means most of the energy coming in, this has got an energy coming in. Most of the energy is absorbed. We notice over here, let me just put him up, we notice a stream of electrons start flowing. So we get a current flows. So this incoming light must have knocked an electron out of an atom somewhere, out of an orbital, and when it did so, that electron was then able to flow as a current and obviously do work for us, like power the little car engine. Now, if you've ever played with one, you'll notice that when it goes under a cloud, it slows down, right? If you put your hand or whatever in front of it, it's not going to go anywhere at all, right? It needs the incident light to activate the electrons to go around the circuit. Now, how does this work? Well, first of all, let's just look at light itself, okay? Let me go back to my black. What you've got is you've got this material. Let's have a look at light. Let's say this is red, okay? Or let's say this is infrared, and this is visible light here, okay? This is visible, and over here you've got, let's say, ultraviolet and gamma is doing this. Okay? The light is moving that way, shining that way. Now, what we do is we've put a pretend bubble around each piece. Okay, the bubble stays the same size. Okay, there they are. All right. So can you see that inside the bubble over here, we've got a little bit of wave. We've got more wave in there. We've got a lot more wave in there, right? So inside this bubble, this packet, we've got a certain piece of wave. This packet, okay, is called a, well, let me redo it. Let's do it let's do it the way that you guys have got it. I'm going to call it a light wave. Okay, has got a photon. Okay, this parcel of energy, we're going to call a photon, and you'll hear this word quantum mechanics, quantum color dynamics, quantum electrodynamics. That is the packet. Quantum means an amount or a packet or parcel of energy. So inside each one of those, we've got that. If you now look at it, obviously, the shorter the wavelength, the higher the frequency. So this here, on this side, right, is going to be short lambda, high frequency. This side is going to be long lambda, low frequency. All right? And if you remember from the wave equation says the velocity is equal to lambda times frequency, but we are talking about light. Therefore, it is c is equal to lambda f, right? The speed of light, this is 3 times 10 to the 8 meters per second over there. That is the speed of light. So that must remain constant. So we've now got our infrared, our invisible light, and our ultraviolet light. So how do we define this process? We say, okay, what is actually happening here? Just make another one. What is happening? This little quantum of energy is coming in. Let me just get my my colors out here. Here we go. Here they come. Okay. Here's the energy. The little package of energy is coming in. It's coming in towards the material which is here. Okay. It's hitting that, and I see electrons going off that way. Well, there's obviously this process. I am altering the structure of the material that I'm hitting with the light. I am, in some cases, I am ionizing. Because what is ionizing? we are creating an ion. Okay? You'll see this often in questions involving gases. All right? As it passes through, it's going to create an ion in the gas. Now, let's just say here, all right, let's just consider this now. This is my little quantum of energy. Now, how much energy is inside there? Well, the energy is equal to H times F. That over there is called, I was going to write the word max, but let's just call it Planck. It's actually Max Planck. Planck's constant, okay? That is Planck's constant. And you get given at 6.63, I think. I may have got it down here. Now, the energy inside my little package is equal to that, and that is the straightforward frequency. That's the frequency that we use. Now, what does that mean? It means the higher the frequency, so a high frequency means lots of energy. Doesn't it? A low frequency means low frequency, low energy. Right? Remember, you can also say C is equal to lambda F, therefore F is equal to C over lambda, therefore the energy of a photon is H times frequency I can write as C over lambda. You will see it in your table as HC over lambda. Okay? It's the same equation. Okay? You're only going to use these two equations currently. So, now, this energy, let's just think about it. If any of you have ever played snooker or pool, you know the balls are arranged in the triangle, right? Let us now say this is the ball that I'm going, the cue ball or the ball we're going to hit the triangle with. We've got a couple of options. The first option is I can hit it and just roll it so that it just touches the others and gives them a rattle. Correct? So I can do that. Now, that is the amount of energy that I am giving the cue ball. So I say, for example, yep, here's my triangle and there's my balls inside my triangle. So what do? I hit it with my incident ball, okay, and it just basically, it just rattles the cage, all right? So inside here, the energy has been absorbed of this ball and it's just rattled everybody, okay? So what it's actually done is it's actually lifted possibly an electron in an orbital, has been affected, lifted up, and then dropped down again. All right? The next option that I can do is I can say, right, here's my stack. So now I come along and I hit it with my ball, and one ball just pops out. So this option here is just pops the ball out. So it just pops the ball out, right? So in other words, my triangle would be there, the ball just comes on the outside. That is significant in the photoelectric effect. What is the third option? The third option, now I know purists are going to say, yes, but hang on, all the balls are going to fly. Let's just pretend only one comes out. So what happens is I hit it so that it does this, and I hit it there. There is my incident ball, incident wave, and this ball flies off or moves away, right? This ball is moving. What kind of energy has something got that's moving? Kinetic. So this has got EK, it's kinetic energy. And that is a half mv squared, right? M of what? The mass of an electron, okay? You get given it. It's very small. kind of think something times 10 to the minus 31 kilos. We've got it in the examples. It's not to worry about at this point. So what have we got here? We've got the three options. Now, in the first option, which we deal with the absorption, we're going to be raising the level of electron in orbitals up, okay, and then it falls down and then it emits the light. The second part is that we just have enough to carry it over the threshold. This is the threshold. Okay, threshold frequency. Never mind, we'll talk about that now. So what is happening here is that it removes the electron and just pops it onto the surface. So if we're looking at it now in terms of an electron, let's just have a look at our electron, shall we? Okay, what happens to it? Here we go. All right. Now my light comes in, my package, my quantum, my photon, here it comes. It comes in and then it just lifts the electron onto the surface. That is called the threshold. Or it lifts and kicks. And the electron goes off with a velocity. Right? So what does it mean? It means that the electron has been given sufficient energy to dig it out. There we go. I've dug it out of the metal. Okay? And I've given it a kick. The amount of energy needed to dig it out plus the amount of energy that is left over gives it the kinetic energy. So we can then say, oops, I'm running out of space here. Just go down a bit. Okay. So I've got my energy inbound, which is my photon. That must be equal to energy after or outbound, if you like. Right? So energy inbound we know is HF. Right? That we've got two pieces of energy here. We have got enough energy to lift it to the threshold, plus we've got kinetic. Right? The energy to lift it to the threshold we call W. It's got a name. It's called the work function. And this one here is EK. Now, just to take it the last step, HF is equal to work function W0 plus a half mv squared. This work function here, let's just examine that. What do I mean? I mean that's the energy needed, the work function. Work function is the energy needed to lift an electron to the surface, but no EK. It doesn't get the electron to move. All right? So what do? We say, right, that's the work function. This is the energy to dig it out and put it over there. Then if there's energy left over, it's going to give it a kick. So the amount of energy left over depends upon, is going to tell us how fast the electron is going to move away. Okay. Now, let's have a look at one more thing. All right. Let's have a look at the difference, the intensity. Okay. The intensity. Okay. The intensity. The intensity means more photons. Okay. So instead of this, I've got 10 of these coming in. Each photon, I'm going to put this down, one photon interacts with one electron. Okay. So one photon goes to one electron. Now, therefore, if I've got lots of photons, I get lots of electrons. Lots of photons gives me lots of electrons. It's as simple as that. Now, if that is the case, right, if I push my intensity goes up, then my current goes up, right? The more photons, the more electrons. So intensity is linked to current, right? Similarly, it's going to affect the ionization energy as well. All right. Oh yes, and here's a word I wanted to put up is irradiated. The word itself, irradiated, means light shone on it. Just so we get the terminology right, right? The irradiated is the light is shone on it. Now, let's just go back to this work function, okay? This W0, this work function, right? That's the energy to dig it out. W0 is joules. All of this is joules, hey? Now, yes, they are very small numbers in joules, but they are joules. What do I do now? I say, okay, the work function itself is, well, it's very particular to a specific metal. Okay? Each metal has got a different work function because it depends upon, obviously, the electron configuration and the atomic structure, how tightly it is held, right? And can I take that electron away? And hence, obviously, create the ion. Now, the work function. I mentioned the word threshold, and I did add a frequency to it at some stage. This is the energy. If I just look at this, bear with me. This here is the energy in, which is HF. Then we said we split it. I'm just going to split it. Let me just take it sort of like that. I've split it half-half. It's obviously not going to be half-half. We said that part of the energy goes to EK, which is the half mv squared in joules, right? Now, but before we can do that, we have to overcome the work function, also in joules. So therefore, this HF inbound must be split into bits. This is called HF0, where F0 is called the threshold frequency. Threshold frequency. This is the frequency where it's just enough to dig the electron out and put it on the surface. Okay? That's all it does. So the work function is the amount of energy. So all we've done is we've associated a frequency with it. That's all it is. It's no big deal apart from that, right? We've got the energy in. Some of it goes to digging it out. That's HF0. So the balance is the kinetic energy component that is sent away. Okay? What I'm going to do is I'm going to just leave it at that one, because then next we're going to do the photoelectric cell, and we're going to do some definitions, an example or two, and then I'm going to discuss an experiment, okay, where we have to plot the graph. I don't see it in my book, so I'm going to have to put that one in. Okie dokes. I'm just going to leave it at that point, and we'll come back and we'll carry on with the photoelectric cell itself and a couple of examples. Cheers. It's a nice section of work, not too difficult. Bye.